Welcome to Lesson 2.2 Installing Unsloth on Windows. Learning Objectives. 3 separate Python environments power this course, and keeping them straight will save you hours of debugging. The Win environment runs on Python 3.13 and handles video production, MoviePy, Matplotlib, Pillow. The fine-tuning environment is a Conda environment on Python 3.11, and this is where everything in the current lesson lives. Torch, Unsloth, Transformers, Heft, Chur. The VLMIAMV environment, also Python 3.11, handles model inference via a VLLM server with an OpenAI compatible API. One critical rule: the two libraries have conflicting PyTorch requirements, and mixing them breaks the inference server. Keep them isolated and you'll never have to untangle a dependency conflict. Each environment has a dedicated activation script, so you never have to remember long conda or vem commands. For video work, run tokens, electronic domain, activate video.ps1, and then call your. For fine-tuning, which is where you are right now, run tokens, electronic domain, activate training.ps1, then conda activate fine-tuning. For inference, call the VLLM python binary directly at gvllm python.exe with the pnm VLM flag. Using them consistently means the right packages are always in scope when you run a command, which eliminates an entire category of "it works on my machine" confusion. By the end of this lesson, you'll understand exactly where Windows differs from Linux for Unsloth, and why those differences are smaller than you'd expect. You'll install Unsloth successfully, handle the flash attention and Triton warnings without panic, test that everything works, and have a clear playbook for the most common installation errors. Nothing here is exotic. It's a straightforward setup, and you'll finish it with a fully working fine-tuning environment. Windows Reality Check. The feature comparison between Windows and Linux comes down to two missing components: Flash Attention 2 and Triton kernels. Everything else, LoRa, QLoRa, 4-bit quantization, the full training API, is identical on both platforms. The speed numbers reflect this. Linux reaches 2.0x over standard PyTorch, Windows reaches 1.8x. Memory usage is 30% on both. If maximum throughput is critical for your use case, a Linux environment will give you that extra 10%. For most fine-tuning workflows on a development machine, Windows at 1.8 times is entirely practical. The quality of the trained model is unaffected by the platform. Only training speed differs. Before touching a single command, here's the honest picture. Unsloth has a few Linux-only optimizations, Flash Attention 2 and Triton kernels, that simply don't compile on Windows. That costs you roughly 10 to 15% of peak speed. Everything else? Identical. LoRa, QLoRa, 4-bit quantization, all the core training machinery, fully functional on Windows. You're still looking at roughly 1.8 times faster training and 70% less memory compared. The gap between Windows and Linux is real but small. Don't let it stop you. Installation methods. The installation flow for Windows follows 4 steps. Activate the fine-tuning conda environment. Install PyTorch with the CUDA 12.1 index URL. Install bits and bytes. Then install Unsloth from GitHub with the Q121 extra specified. During that last step, you'll see the flash attention warning. That's expected. Ignore it. Once all 4 steps complete, run verify_unsloth.py. A clean output means you're done. If the script surfaces errors, the troubleshooting section of this lesson covers the most common ones with specific fixes. The flow is linear, and each step confirms the one before it, so failures are easy to localize. The single command install pulls Unsloth directly from GitHub and tells pip to grab the CUDA 12.1 compatible build. The bracket notation, Unsloth, is a pip extra specifier. It activates a set of optional dependencies tuned for your specific CUDA version. The git plus prefix means pip clones the repository and builds from source, rather than fetching a static package from PyPI. This gives you the latest code and ensures the CUDA bindings are correct for your hardware. On Windows, Unsloth's own install logic detects the platform and automatically skips flash attention. You don't need to configure anything for that. If the single command install fails, the two-stage approach gives you more control. The first command pins PyTorch decision and torch audio to CUDA 12.1 builds from PyTorch's own index. This sidesteps any version mismatch between PyTorch and your drivers. The second command installs the supporting libraries: transformers for model architecture, datasets for data loading, accelerate for distributed training utilities, PEFT for parameter efficient fine-tuning, and TARL for the reinforcement learning from human feedback trainer. Once those are confirmed working, the third command installs Unsloth itself. Splitting it this way means if something breaks, you know exactly which layer caused it. The virtual environment approach is the cleanest option for a development machine where you want multiple projects to coexist without dependency conflicts. The first command creates an isolated Python environment named Unsloth and VEF. Activating it changes your shell context, so every pip install from that point forward lands inside the environment, not in your system Python. Notice the prompt changes to show the environment name. That's your confirmation it's active. The PyTorch install targets CUDA 12.1 explicitly via the Q121 index URL, and then Unsloth is pulled from GitHub on top of that verified base. Anything installed here is completely separate from your other Python projects. Step-by-step installation. 3 setup commands before Unsloth itself. First, navigate into your project folder so relative paths work correctly throughout the rest of the course. Second, create a virtual environment. This is optional but strongly recommended because it gives you a clean slate you can always delete and recreate if something goes wrong. Third, upgrade pip. Older pip versions sometimes mispass the extra specifier syntax that Unsloth uses, so a fresh pip eliminates that class of failure before it happens. This one-liner is your sanity check before installing anything else. It imports PyTorch, prints the version string, and then reports whether CUDA is reachable. Run it in PowerShell by calling Python with the -c flag. What you want to see: a version number like 2.6.0 and the word true. If you see false for CUDA, stop here. Unsloth can't use your GPUs until PyTorch can see them. Go back to lesson 2.1 and re-verify your CUDA installation before continuing. The output you're looking for is PyTorch 2.5, 1 later, followed by true. That true is the critical signal. It means PyTorch has found your CUDA runtime, enumerated your GPUs, and confirmed it can dispatch work to them. If you see a different PyTorch version, that's fine as long as it's 2x. If CUDA shows false, your driver or CUDA toolkit installation needs attention before proceeding. Now install Unsloth itself. This command fetches the repository from GitHub and builds the Q121 variant. The same command shown in method 1, now running inside your verified environment. The build pulls in all remaining dependencies automatically. Expect this to take 5 to 10 minutes depending on your internet connection, since it's cloning a repository and compiling package metadata. Watch the terminal as this runs. You'll see pip clone the Unsloth repository to a temporary build directory, then collect and download its dependencies. Packages like transformers, bits and bytes, and tokenizers with their exact version numbers and download sizes. The final lines should read, "Successfully installed Unsloth." followed by a list of every package that was added. That list is your confirmation that the dependency graph resolved cleanly and nothing was skipped. 3 warnings will appear on Windows, and all 3 are expected. The first 2 tell you that Flash Attention and Triton are unavailable on this platform. Unsloth detected Windows and skipped those components automatically. The third warns that Xformers is either absent or version mismatched, so Unsloth will fall back to PyTorch's built-in attention implementation. None of these prevent Unsloth from working. They're informational messages, not errors. Your training will run. It will just be operating at Windows native speed rather than peak Linux speed. This verification script does 5 things in sequence. It imports Unsloth and confirms the import succeeds. It prints version strings for Unsloth, transformers, and PyTorch so you can confirm compatibility at a glance. It checks CUDA availability and prints the name of your GPU. You should see Tesla P40 here. It loads a small quantized model to confirm that the full inference stack works end-to-end, and it reports GPU memory consumption after loading, which gives you a baseline for what a minimal model costs. If any step fails, the script catches the exception and prints a targeted error message pointing you toward the fix. A successful run looks like this. Each step prints a confirmation. Your GPU name appears in the CUDA check, the model loads without errors, and memory usage is reported in megabytes. The number to watch is GPU memory after loading. For a small test model, it should be well under 2 gigabytes. If you see your Tesla P40 listed and memory usage in a sensible range, the entire stack from CUDA through Unsloth is working correctly. The verify_unsloth.py script in the notebooks/00 setup/folder runs a more thorough check than the quick inline test. It validates Triton availability, confirms LoRa patching is active, checks every package version against known good ranges, and does all of this without downloading a model, so it completes in seconds. Run it anytime you change your environment and want a fast confirmation that nothing has broken. This is what a clean installation looks like. Every line shows a green OK marker. Unsloth imports cleanly. PyTorch and CUDA versions are confirmed. Both Tesla P40 GPUs are detected and listed by name, and the supporting libraries PFT, TRL, transformers all load without issues. Notice the 4-bit quantization confirmation at the bottom. That tells you bits and bytes is working correctly with CUDA, which means QLoRa is available. If your output matches this pattern, you're done with installation. Everything you need for the rest of the course is in place. Common installation issues. Vulzuk yon ma. Some sits use. Vulzuk yon use. Vulzuk. 5 errors cover the vast majority of Windows installation failures. Module NiceOut4 for Unsloth means you're in the wrong virtual environment. Activate the correct one and reinstall. CUDA error, no kernel image, means your PyTorch build doesn't match your CUDA version. Reinstall PyTorch with the correct CUDA index URL. A bits and bytes CUDA error usually means the wrong bits and bytes version. Pin it to 0. 43.1. An emport for Triton is expected on Windows. Set the environment variable unsloth_compile_disable=1 to suppress it. SSL or proxy errors on corporate networks require the trusted host flags on your pip. Each of these has a direct one command fix. None of them require reinstalling Windows or your GPU drivers. A module snider4 for unsloth.fast language model means Python can't find the unsloth package in the current environment. This is almost always an environment mismatch. You installed Unsloth in one virtual environment, but you're running Python from a different one. or from the system Python entirely. The import failing here doesn't mean the installation is broken, it means you're looking in the wrong place. Two commands fix this. First, run pip show unsloth to check whether the package exists in your current environment and where it's installed. If that returns nothing, Unsloth isn't here. Second, force a reinstall with the force reinstall flag pointing at the GitHub source. This overwrites any partial or corrupted installation. Before running either command, confirm you're in the right virtual environment. Your prompt should show the environment name in parentheses. If it doesn't, activate it first with when we scripts activate. This error, CUDA out of memory, failed to allocate, means your GPU ran out of VRAM during the installation test. With 24 GB per card, this is unusual for a small test model, which points to another process holding GPU memory. The allocation size in the error message tells you how much was requested when it failed. If that number is large, the test model itself may be too big for the default configuration. Run NVIDIA-SMAE first to see what's currently consuming GPU memory. Look for processes in the lower panel. Any application holding hundreds of megabytes is a candidate to close. If another Python process from an earlier test is still running, kill it. Once memory is clear, open test_unsloth.py and change the model underscore name to unsloth/tinylama BSPNB 4-bit. This is a 1.1 billion parameter model that fits comfortably under 2 GB, making it the right choice for verifying your installation without the CUDA setup warning from bits and bytes means the library loaded but couldn't initialize its CUDA kernels correctly. This is distinct from PyTorch not seeing CUDA. PyTorch may be fine while bits and bytes fails independently. The most common cause is a version mismatch between bits and bytes and your CUDA runtime. Until this is resolved, 4-bit quantization won't work, which means QLoRa training won't be available. This one is worth fixing properly rather than working around. The fix is a clean reinstall of bits and bytes. Uninstall the existing version first, then reinstall with no cache dir to force pip to fetch a fresh copy from the network rather than reusing a potentially corrupted cached wheel. After reinstalling, verify immediately with a one-liner python -c import bits and bytes, print bits and bytes does our versions was. If that prints a version number without errors, bits and bytes is now correctly linked. If the latest bits and bytes build still fails, pin it to version 0, 43.1, a known stable release with solid Windows CUDA support. Specifying an exact version with the == operator tells pip to install precisely that release rather than resolving to the latest. This is a reliable fallback when a newer version has a regression or an incompatibility with your specific driver version. Failed building wheel for tokenizers means pip tried to compile the tokenizers Rust extension from source and couldn't. The tokenizers library is written in Rust, so building from source requires both a Rust toolchain and a C++ compiler. On a fresh Windows machine, neither is present by default, which is why this fails. The fastest fix is forcing pip to use a pre-compiled binary wheel instead of building from source. The only binary, all flag, tells pip to refuse source distributions entirely. If a binary wheel exists for your platform and Python version, it installs in seconds without needing any compiler. For tokenizers, pre-built wheels exist for Windows and all common Python versions, so this approach almost always works. If pre-built wheels aren't available for your configuration, you'll need the actual build tools. Download the Visual C++ Build Tools installer from the Microsoft URL shown here. Select Desktop Development with C++ during setup and then retry the Unsloth installation. That workload installs the MSVC compiler and Windows SDK that Rust's build system needs to compile native extensions. And importantly, about a missing DLL, when importing a Python module means a native library dependency isn't present on the system. This is different from a missing Python package. The Python package is installed, but a Windows DLL it depends on at runtime isn't found. The two most common culprits are the Visual C++ redistributable runtime and a corrupted PyTorch binary. Fix this in 2 steps. First, download and install the Visual C++ redistributable from the Microsoft URL shown here, then reboot. This installs the MSVC runtime DLLs that PyTorch's native extensions depend on. Second, do a clean reinstall of PyTorch. Uninstall all 3 packages, Torch, Torch Vision, Torch Audio first, then reinstall from the PyTorch CUDA 12.1 index. The uninstall then reinstall sequence matters. Leaving a partial installation in place and running install on top of it can leave mismatched binaries on disk. Get is not recognized as an internal or external command, means get isn't installed or isn't on your path. This blocks any pip install that uses a get plus URL, which includes the Unsloth install command. Without get, pip can't clone the repository. Install Git using winget with the command shown here. Winget is Windows' built-in package manager, available on Windows 10 and 11. After installation completes, restart PowerShell. This reloads the path environment variable so the Git executable becomes visible to your shell. Confirm it worked by running git ditch version. You should see a version string like 2 x.x. Once that's confirmed, retry the Unsloth install command. An SSL certificate verification error means pipe couldn't establish a trusted HTTPS connection to GitHub or PyPy. On corporate networks, this is often caused by a firewall or proxy that intercepts TLS traffic and presents its own certificate, one that pip's certificate store doesn't trust. Antivirus software can cause the same behavior. The trusted host flags tell pip to skip certificate verification for the specified hosts. This gets the installation unblocked, but treat it as a temporary workaround. You're disabling a security check. The right long-term fix is to add your organization's root certificate to pip's certificate store, or to temporarily disable the proxy or antivirus for the duration of the install. The trusted host approach is fine for a development machine where you control the network. Avoid it in any production or shared environment. Verify complete installation. This comprehensive verification script works through the installation systematically. It checks the Unsloth import, then validates version compatibility across transformers, PyTorch, and bits and bytes, flagging anything that falls outside the tested range. It enumerates your GPUs by name and VRAM capacity, tests that bits and bytes can initialize its CUDA kernels, and then loads a small model to confirm the full inference path works. The final output is a pass/fail summary. If every check passes, you see a confirmation message and you're ready to move into actual training. If anything fails, the script tells you which component failed and what to investigate. No guessing required. Run the script from your project root with the command shown. Watch each line as it executes. The checks run sequentially, so if one fails, the ones below it may not run. A clean run prints a success message for every component. Any failure prints a specific error and a suggested fix. Address failures from top to bottom. Fixing a dependency issue early often resolves apparent failures further down the chain. Performance expectations on Windows. The performance chart makes the trade-off concrete. Standard PyTorch is the baseline. Unsloth on Linux doubles it. Unsloth on Windows reaches 1.8 times 90% of the Linux result. Both Unsloth configurations use 30% of the memory that standard PyTorch requires. That memory saving is the more important number for most workflows. It's the difference between fitting a 7 billion parameter model on a 24 GB card and not fitting it at all. The speed advantage is real and meaningful for long training runs. For the purposes of this course, Windows performance is more than sufficient to complete every exercise efficiently. Here's the concrete comparison. Standard PyTorch fine-tuning is the baseline at 1.0x speed and 100% memory usage. Unsloth on Linux reaches 2.0 times speed at 30% memory. Unsloth on Windows reaches 1.8 times speed, also at 30% memory. The memory savings are identical across platforms. The speed difference between Windows and Linux is 10%. What matters most, you're getting 1.8x faster training and 70% less memory than the standard approach on hardware you already have without changing your operating system. The three things Windows is missing are Flash Attention 2, which costs about 10% speed, Triton kernels, which cost another 5%, and a handful of Linux-specific CUDA optimizations. Everything else is fully available. LoRa and QLoRa work perfectly. 4-bit quantization works perfectly. Fast inference works perfectly, and every training feature in Unsloth is accessible. The Windows limitations are real but narrow. They affect peak throughput, not capability. Optional. Advanced installation. Xformers is an optional memory-efficient attention library that can recover some of the speed lost from not having flash attention. Install it with pip and then verify it loaded correctly by importing it and printing the version. If the version string appears, Xformers is active and Unsloth will use it automatically. If the install fails or produces errors, skip it. Unsloth falls back to PyTorch's built-in attention without any configuration change on your part. The gain is 5 to 10% if it works. The cost of skipping it is nothing. The final optional step registers our dedicated Jupyter kernel for your Unsloth environment. The first command installs Jupyter itself along with IP widgets for interactive notebook controls and IP kernel to expose your Python environment to Jupyter. The second command registers the kernel under the display name Unsloth. This is what appears in the Jupyter kernel selector when you open a new notebook. The user flag installs it for your account only, avoiding any permission issues on a shared machine. After this, every notebook you open can select the Unsloth kernel and have direct access to your fine-tuning environment. Installation checklist. Why days? Before moving to the next lesson, confirm each of these. PyTorch with CUDA verified. You saw true from the CUDA dot is underscore available asset check. Unsloth installed via pip install Unsloth. The import from Unsloth import fast language model completes without error. Our test model loaded successfully. GPU memory after loading is under 2 GB. No critical errors appeared. Warnings about flash attention and Triton are fine. And verify underscore unsloth.py passes all checks. Every box checked means your environment is solid and you're ready to build on it. Key takeaways. 8 things worth remembering from this lesson. Unsloth works well on Windows. The Linux speed advantage is real but small. Flash attention warnings during install are expected and harmless. Triton not being available on Windows is by design, not an error. Always test with a small model first. Quinn 2.5-0.5b or Tiny Llama keeps iteration fast. A virtual environment keeps your dependencies clean and your system Python untouched. Most installation failures trace back to PyTorch or bits and bytes. Check those first. You still get 1.8 times the speed of standard fine-tuning, and QLoRa with 4-bit quantization is fully functional. The most important feature works perfectly. Next lesson, Unsloth is installed and verified. In lesson 2.3, you'll set up Jupyter Lab, the interactive environment where you'll write and run all your fine-tuning code going forward. If you hit any issues after this lesson, the Unsloth GitHub issues page and the Unsloth Discord are both active communities with Windows-specific threads. The Bits and Bytes repository also has a Windows troubleshooting section if quantization gives you trouble. You're past the hardest setup step. The next lesson is straightforward.